Let's connect transition rates, entries of the generator, to exponential random variables. So we're going to do it on this example here. This is a transition rate diagram for a three-state CTMC, and we've already been able to compute the rates for every state. This determines how long we stay for in state 0, 1, and 2. And then this these embedded chain one-step transition probabilities told us once every single waiting time is over, here's where we go to next. Let's now give a little bit of interpretation for the RxYs in terms of rates of exponentials. And to do this, let's review what we already know. One thing we know is that if we're in state 1, we're going to wait there for an exponential amount of time. That's going to be called tau 1. And that exponential has rate R1. So we know this. The second thing we know is that the embedded chain is going to tell us where to go to next. And B10 and B12, which we've computed above, so here's B12, here's B10. The sum of these is 1, so we know those are the only two possible transitions, either going to state 2 or going to state 0. And that's the way we're accustomed to thinking about this. And here's a different interpretation, so another interpretation. And this is going to be in terms of two competing clocks. There are going to be two waiting times, tau 10 and tau 12, and the first one, the one that happens before the other, is going to win and determine where this CTMC goes. So here's a summary of this. Again, this right here basically says that our general kind of previous way of thinking about this was in state 1, we're going to stay for time tau 1, distributed exponentially with rate R1. And now we're going to think about it differently. We're going to think of it as two clocks, two waiting times. One of them tau 10 and one of them tau 12. Both are exponential. Tau 10 is going to have a rate associated with the arrow from 10, this one right here. And R12 is going to be associated with the rate from 1 to 2. And so we have these two clocks. They're independent of one another. And we're just going to take the minimum and try to see whoever wins, that's the one that's going to determine the transition. So if the clock for tau 10 kind of comes first, if tau 10 is smaller than tau 12, then it's the transition to 0 that's going to win, and that's going to determine where the CTMC goes. But if the clock for tau 12, if this waiting time is smaller, then it's the transition to 2 that's going to win, and we're actually going to go to state 2. Eta 1 is just a definition of this minimum. So we're going to see, we're going to kind of investigate now what this random variable is. It's the minimum of, these two independent clocks. So they're going to be independent waiting times. And now let's look at the distribution to see if we can give some interpretation for what this random variable is. And there's always a certain trick to looking at distributions of minima of random variables. And the trick is, if you have a minima, you want to look at the survival probability. If you have a maxima, you want to look at the CDF. Here I have a minima. I'm going to look at the survival probability, and here's the reason. So in this step, I haven't done anything. I've just plugged in my definition for eta. The next step is the crucial one. It says that if the minimum of two things is greater than t, then both of them had to be greater than t, right? So if you have 2 times, both of them are, or if the smallest of them is greater than t, then both of them had to be greater than t. Because they're independent, I can now take this joint distribution and split it up into a product of two marginals. And we know what those are. Those are two survival probabilities for two exponential random variables. One of them had rate R0, the other one had rate R12, and you plug it in and this is what you get. Let's look at the CDF. The CDF is right here. It's just 1 minus the survival probability. We look at the exponent here. It's R10 plus R12. That sum is exactly summing up over all the arrows leaving state 1. This one and this one. And therefore, it's equal to little r1, the rate out of state 1. And therefore, this is equal to the distribution of tau 1, the waiting time in state 1. So what happened is that with a kind of a different logic in terms of clocks associated to every single arrow in this diagram here, we were able to reproduce the original intuition of waiting in every state for some specified exponential with the rate associated to that state. And so let's see, this is kind of the conclusion of this part. It's saying that eta constructed as such is basically in distribution at least the same thing as tau 1. We're able to construct a clock of rate R1 from two clocks described by the rates given to us by the generator. And now the question is, which one of those actually won? We know that the kind of the time of the win occurs at time eta 1, that's great, but which one actually beat the other? Which one was the smallest one? Because the reason we need to know this is because the one that is going to be the smallest one is going to determine where the CTMC goes to next. So in other words, if tau 10 is the smallest, meaning that it's equal to eta, then we're going to transition to state 0. And conversely, if tau 12 is the smallest, meaning tau 12 is equal to eta, then we're going to go to state 2. So in here, we're going to look at one of those. The sum of those is going to be, the sum of those two possibilities obviously going to be 1. So we only need to look at just one of them. What is the probability that the clock associated with tau 10, the transition to 0, wins? And this is the probability we're going to have to work out. So let me work you through that calculation. So one suggestion is always, if you have probabilities and it looks complicated, computing them looks complicated, you always want to switch over to the language of expectations, where you can use properties of a conditional expectation, property of a regular expectation. The tower property is often very useful. This is exactly what we're going to use in this example. So we first transition over from probability to expectation. The probability of an event is the expected value of the indicator of that event. That's what happened in this line. In the next line, I'm now going to simplify the calculation to work with, instead of two random variables, I'm going to work with just one of them. So instead of working with tau 10 and tau 12, I'm going to work with just one of them at a time. So I've used the tower property here, conditioning on tau 10. Could have done it the other way. I think both are valid. And now to break things up into kind of more systematic steps, I've defined this function g in terms of this inner expectation. So I have, the tower property always gives me an inner and outer expectation. I'm going to take the inner one, and use it to define this function g. That's the expectation of tau 10 being less than tau 12, conditioned on tau 10. So what is that? That's, it's the same thing as this probability, and further, by the fact that the clocks were independent, it's just the probability that tau 12 is greater than t, and we know what that is. We know the rate of tau 12. The rate of tau 12 is R12, and so you get this formula for the inner expectation in the tower property right there. So this allows us to skip ahead to this equality right here. So I've written it in terms of g of tau 10, and I'm plugging in directly what that means in this step right there. I've already computed the function g, right? I've computed it to be this guy right here, and therefore I'm just going to plug it in, and what's left? What's left looks like the moment generating function of tau 10 with the with R12 as the parameter, right? And so this is what a moment generating function for an exponential random variable would look like. And now I'm just going to do a plugin. So instead of theta, I have R12, actually negative R12. And my random variable here was exemplified by tau. In there, it's tau 10. That one has rate, instead of mu here, it has rate R10. And so all I'm doing is I'm plugging in things directly from above So I had mu in the numerator before, that's my R10. I had R10 plus, sorry, I had mu minus theta on the bottom, that's the same thing as R10, minus R12, which is the same thing plus R12. And so what you'll notice is that you get the same exact probability as the one given to us by the embedded chain. The probability that transition 0, 1 was the same as B10, the embedded chain probability of going to 0. Right? This is what we obtained. And so this is a different way in terms of the generator and its transition rates to think about how this CTMC will evolve over time. You can think of it as transition rates for each state and the embedded chain, or you can use this notion of clocks for every single arrow in the transition rate diagram, so for every single transition rate in the generator, and these clocks compete to determine which state we're actually going to go to next. And this would be, kind of a more generalized version of this. All right, this is basically going to take care of any scenario that that you have, that you could possibly think of. Even a scenario with infinitely many states, you can even kind of translate all of this. Here I have n possible transitions. We could think of kind of n going to infinity and have infinitely many of them. That's going to be fine in that setting as well. But here, we have a state x that we're in. There may be some, transition rates into it. We don't really care about those for now. What we care about is the fact that from state x, the transition rate diagram, and hence the generator, is telling us that we can go to state 1, state 2, state 3, all the way up to state n. And the entries of the generator, the transition rates, are going to tell us the rates at which this happens with. And those are going to be Rx1 all the way through Rxn. Therefore, Rx is the rate of transition out of state x. So we wait in state x for an exponential amount of time, but rate Rx. And then, according to our previous formula, we know that these are the embedded chain transition probability is telling us where we go to next. And now we can think about the same exact explanation, the alternative explanation, is that of each transition from x to I. So one of these, 1 through n, I could be 3, for example. We have an exponential clock, tau x1, of rate prescribed by the generator, the transition rate from x to I. We're going to let that clock run and pick the smallest tau xj to select the next state. It's just an alternative way of thinking about this. One way is we stay in state x for some amount of time and use the embedded chain. The other way is to run all of these clocks for every single possible transition in the diagram and pick the winning clock. And so right here, this probability right there is easy to come by. It says that the minimum of all of these exponential clocks is the same thing as one clock with rate that's the sum of them. And on the other hand, if we want to determine that clock J1, meaning tau xj, is literally equal to the minimum of all of these, that's going to turn out to equal to the embedded chain transition probability to j. The way to select the smallest of n exponential clocks with rates R1 through Rn is to put the one that won, the rate for that on the top, and divide by the sum on the bottom. And the calculations are identical. Here's the first calculation. Why is the minimum of the sum of the minimum of n exponential clocks with rates Rxi's equal to one with a cumulative rate Rx? Why is this true? Right? In other words, why is it that waiting for the first one of these, n to fire is the same thing as waiting for one of them with the rate little rx to fire? Well, that's the same calculation we already ran through. We're looking at the minimum. We're going to look at the survival probability. If the smallest of n things is greater than t, all of them had to be greater than t. By independence, we're going to split them up into a product of marginals. These are just, the expressions for survival probabilities of each exponential. We're going to sum up the rates and see that that's exactly the survival probability of tau x, the exponential with rate rx staying in that state. So the independence here was crucial, of course, and this example is, literally the same exact calculation as in the example of 2 clocks that we already did. This is a quick note. For the maximum, we would actually do something like this. So we look for the survival probability when we look at minimum, and we're going to look at the CDF when we look at maxima. But that's just a separate note. And here's the big giant calculation for figuring out which one of them won. How do we know that exponential j, clock j, wins? So we would need to have the waiting time be the smallest of all of them. And that's going to turn out to equal to this ratio. You take the rate for the winner, rxj, and divide it by the sum of the rest. And this is an identical calculation. Again, use of the tower property right here, writing out the inner expectation as a function g, which is just a convenient way to break down the calculation. You get to this exact same step as before. The only difference is that in this moment generating function, you now have sort of a sum of things as opposed to just one other clock to deal with. But the formula for the MGF remains the same, and you get to the same exact result. So I'll let you review this kind of calculation in detail if you like, but it parallels the one for the 2 clocks and simply says that if you have n clocks and you want to pick the winner, right, which one of them happened first, the tau xj is the winner with probability equal to its rate in the numerator divided by the rate of the sum on the denominator. And this, of course, as it better, because otherwise we have a contradiction, is in direct correspondence with the embedded chain. So both the embedded chain can, is a way of finding out where the Markov chain goes next, but so is this approach with many, many clocks, and whichever one, goes first is the one that's going to determine the transition to a particular state, whether it's 1 or 2 or so on and so forth.